Hi, I'm Doug Rosenberg. I'm the author of AI Assisted MBSE with SysML. And today I want to talk about what it would look like if we had a MagicGrid-like process view for AIM process. So if you're familiar with MagicGrid, the layout of this grid should look familiar. It's basically the four pillars of SysML. It's the columns. That's requirement, structure, behavior, and parametrics. And then the rows are the life cycle phases that we're going to go through in our SysML model. So conceptual modeling, logical architecture, physical architecture, implementation, and test. And I'm going to be popping back and forth between the grid and the book. So I've got the book open here, and you can see our table of contents here on the left. And what I want to point out is a couple things. Number one, the parts of the book. So part two, conceptual modeling, maps to this top row. And we have logical and physical architecture. That's part three of the book. And then we have software, code generation, and test are going to map to the final two columns on the grid. Now, the presentation of MagicGrid is actually very brilliant because it is a great way to visualize how we're covering all the parts of the SysML model across all phases of the life cycle. What's different about our process, AIM process, is that we include software as a holistic, very important first-class citizen part of our model. And in particular, that impacts the behavior model, so the behavior pillar of our four pillars of SysML. And what that reflects is that in the real world, most of or much of your system behavior is going to be realized in software. And that's different from most of the other SysML MBSE processes that you may be familiar with, and that including MagicGrid. So we're going to focus here on the behavior part of the model. So we're going to do use cases, operational concepts, use case narratives, user interface wireframes, state machines that go across subsystems, state machines within subsystems. We're going to generate microcontroller code, and we're going to generate database code, user interface code, and test cases. So while the grid format should look familiar if you know about MagicGrid, the contents of the cells in the grid are quite different. So I'm going to move our grid view aside here for a minute and show you kind of how we've done all of this in the AI Assisted MBSE book. So we start with a domain model, and here's a high-level domain model for our electron microscope example, which is a single example in our book. And we go into more details, and we come up with, at the end of the chapter, not just a domain model, but a project glossary. So here's a more detailed domain model. Next, we're going to go into use cases, and we're going to talk about using AI both to identify our use cases and to write the use cases. And we're going to discuss different kinds of use case templates. Towards the end of the chapter, what we're going to look at is a way to have AI not only generate the use case, but generate the user interface wireframes for the screens. And we're going to go into requirements modeling, and we'll start out with kind of some basic requirements for the electron microscope. And then we're going to go into a couple of different kinds of prompting We call it deep dive prompting, one of them deep dive prompting. So we're going to deep dive here into the image processing part. We're going to deep dive into database requirements. We're going to deep dive into beam control. We're going to talk about measures of effectiveness. So let me put the grid back here for a second. And what you're going to see is that in the conceptual modeling phase, measures of effectiveness, use case diagrams, system requirements, domain models and glossaries, list of screens, that's all the stuff that we're writing about in that section of the book. And we're going to go into the logical architecture section of the book and then physical architecture. So we'll go back to the book here now, and in logical architecture, we're going to talk a lot about subsystems. So we're using AI to identify subsystems. We're going to create block definition diagrams for our subsystems. And then we're going to decompose these subsystems and come up with things like interface blocks and signals and IBDs. And then as part of our logical architecture, this is a top-level state machine for our electron microscope. And we can actually simulate that and then generate C++ microcontroller code for that. So back to the grid again. That's exactly what we're talking about here in the logical architecture phase. But we're simulating activities and cross-subsystem state machines. And down in physical architecture, we're going to do trade studies, component selection, some more detailed state machine modeling, and simulation and generating microcontroller code. So back to the book, components of physical architecture. We're going to go through and talk about microcontrollers, talk about sensors, go into component selection, and then start doing trade studies after we identify some performance requiremements. And we're actually going to do trade studies of real-world amplifiers and other components. And then we're going to go do some simulation. And our simulation is going to relate to signal-to-noise ratio. And here we're going to do a simulation context diagram, and then a parametric diagram, and eventually we will simulate a signal coming out from our electron detector and then being amplified and smoothed by our signal processing. And finally, in the later part of the book, we're going to talk about generating database code, user interface code, more detailed microcontroller code, and then generating and executing test cases for all those things. That's part 4 of the book. So we're going to talk about generating embedded code from state machines. And here's a whole bunch of state machines for the different subsystems of our electron microscope. We've used AI to generate these. And then we can go drill down and get more detail at any time. And then here is the more detailed state machine that we looked at earlier. Then we're going to go into database design. And we're actually going to go build a database for image processing, which is part of our electron microscope. Go into how to set up the database, and then actually insert some images into it, pull the images out, go into our user interface design chapter. But at the end of the day, we're going to use an image processing library called GIMP and actually do some real image processing to enhance the images, adjust the contrast, adjust the brightness, blur the image, sharpen the image, and things like that. And then we'll wrap up with a whole chapter on testing, where we will identify different kinds of tests and use AI to generate those tests. So just to go back to our process grid, what we're covering in our book is all 4 pillars of UML, and we're going to do that across all stages of the life cycle. And finally, we cover all of this material in our AIM training. And so here's our grid again, and then this goes through labs, where you have hands-on labs. And what you do in the hands-on labs is you follow what we've done in the book and rebuild this electron microscope from scratch, following the AI prompting that we've detailed out in all the chapters of the book. So that's a quick look at our process grid, at our book, and at our training. And for more information, you can visit us at parallelagile.com.